Welcome to my YouTube channel. Today is our lecture number 2, and today we are going to describe a linear system described by planes in space. So before moving to linear systems described by planes in space, we first describe what are planes in space. So a plane in space can be described by two objects. One of them is a point through which the plane passes, which is given by P naught. Another one is a normal vector with this representation. So now if I take any other point P in this plane, and if I construct this vector P naught P, then by definition this vector P naught P is perpendicular to this normal vector. And hence if I construct this vector P naught P which is equal to x minus x naught I plus y minus y naught j plus z minus z naught k, then using this condition of perpendicularity, this dot product is 0. And hence if I simplify this further, the equation of a plane in space is given by in 1x plus in 2y plus in 3z equal to d. So a linear equation in 3 variables. Now, as we described in 2D case, if I have planes in space, then we have the following possibilities, that the planes are parallel. For example, if I take these two planes, they are parallel. So it means that they do not have a common point of intersection. And hence the system described by these two planes will be termed as an inconsistent system. I can add a third plane to this system which may intersect these two planes individually, but these three planes do not have a common point of intersection. And hence in this case, the system described by these three planes will be termed as an inconsistent system. The second case is that they may intersect in a line. So if I consider these two planes, they are intersecting exactly at this line. So if I consider these two planes and they intersect exactly at this line, I can add a third plane to it, and once again they intersect in this line. So we have planes which intersect in a line, and intersecting in a line means that they have infinitely many points of intersection. Another possibility is that I have overlapping planes, and overlapping planes of course have infinitely many points of intersection. And the last possibility is that if I consider these three planes, for example these two, and I add a third plane here, so the common point of intersection is exactly 1. And hence the system described by these three planes is once again consistent, but the solution of this system is unique. And hence a linear system described by planes in space is either once again inconsistent or consistent. Inconsistent means that it is described by non-intersecting planes or have no common points of intersection. And a consistent system means that we have either a unique solution intersecting at exactly one point, or we have infinitely many solutions, all planes intersecting in a line, or we have overlapping planes. Now if I go back to my original system that we considered in our previous lecture given by these two equations, and I plot them here, and I notice that the solution of this system is given by this point 0, 1. Now what do? I perform an operation of addition. So once I add these two equations, I have a new equation which is given by y equals 1. And combining this new equation with these two equations here, I have two new systems, and they are described by x plus y equals 1 with y equals 1, and minus x plus y equals 1 with y equals 1. Now if I plot these two systems, what do I notice? That this is the line y equals 1, this is the line x plus y equals 1, this is the line minus x plus y equals 1, and this is the line y equals 1. And we notice an interesting property, And the property is that the solution set of these two new systems is once again the same as the solution of this system. And hence, if we perform this operation of addition over a system, this addition operation preserves the solution of the system. So, if I have a general system Ax equal to b, if I take its augmented matrix, so operations that preserve the common point are termed as elementary row operations. And these operations are of three types. Number one, we can interchange any two rows in this matrix. We can multiply a row by a non-zero scalar. And the third one is that we can add a scalar multiple of one row into another row. Now, once we perform these operations, there are two forms which are very relevant to a system. And the two forms of the matrix which are very important are known as echelon and reduced echelon form of matrices. So, an M cross N matrix A is said to be in echelon form if it satisfies the following properties. Number one, all zero rows are below the non-zero rows. The first non-zero entry, which we call the leading entry or the pivot entry of each row, must be to the right of the first non-zero entries in the preceding rows. So it means that as we go down in the matrix, the first non-zero entry of each row is moving to the right. And the third one is that the pivot entry of each row is 1. So if I consider this example, here I have a 0 row which is appearing above the non-zero row, and hence this is not in echelon form. If I consider this system, then once again this matrix is not in echelon form, because as I go down, the first non-zero entry of this row must appear over here if it exists, and hence this is not in echelon form. But if I consider this matrix, this is in echelon form because the 0 rows are appearing below the non-zero rows. As I go down, the first non-zero entry is moving to the right, and similar is the case with this matrix. If a matrix is in echelon form, the column that contains a pivot entry is called a pivot column. So for example, if I consider this matrix, this is in echelon form. So column number 1 contains this pivot entry. There is no pivot entry in this column number 2. There is a pivot entry in this column number 3, and hence in this matrix we will call this column number 1 and column number 3 as pivot entries. Similarly, in this matrix, column 1, column 2 and column 3 have pivot entries. Hence in this matrix all the three columns are pivot columns. So if in addition to the three properties described for echelon form, a matrix satisfies the following property, that is, all entries in the pivot column except the pivot entries are zeros. So if I take this matrix here, it's a pivot column, it's a pivot column, it's a pivot column. This is not a pivot column. So we notice that all the entries in this column number 1 except this pivot entry are zeros. All the entries in this column number 3 except this pivot entry are zeros. Similarly, this is the case with the column number 4. And hence, if a matrix satisfies this fourth condition, then we will say that our matrix is in reduced echelon form. The number of non-zero rows in the echelon form of a matrix is called the rank of the matrix. So we associate this parameter with the echelon form of a matrix, which will play a very key role in the solution of linear systems. And given a system Ax equal to b with augmented matrix AB, once we reduce this AB into an echelon form matrix, with this matrix we will associate two types of ranks. They are the rank of the overall AB matrix and the rank of matrix A only. That's it for today. Thank you.